All right, so we're going to be starting off with chapter 16 now. This is question 1 from the review questions. And we're moving on to a new topic. And the topic of interest is acids and bases. Acids and bases, we're going to learn we have different definitions for how we define what an acid and a base is. And in particular, the version that we're going to be using quite often in this class is the definition that's called the Bronsted-Lowry definition. Bronsted-Lowry definition. And the basic idea behind this, as will have already seen in class, is that we define acids as proton donors. Proton donors. So if anything in the reaction, we see that on the left side it has some source of hydrogen, and on the right side it has one less of that. We can say that it has donated a proton. On the flip side, we say that a base would be a proton acceptor. So this is a novel concept for most of you guys. Before, we defined an acid and a base through its ability to produce H plus in solution. That's what was our definition in 101. And if you notice, the acid definition is still pretty consistent with that. But, in Chem 101, we used to say that a base, in Chem 101, we used to say that a base was something that produced OH minus hydroxide in solution. And notice that our definition has changed quite a bit. So now we're saying it's something that accepts protons. So this is a slight little difference you have to get over with. So then moving forward, you will see actually that we're going to have more and more definitions of what we define it as an acid and a base. And we're going to be able to encapsulate more chemical phenomena with a more general definition of what we call an acid or a base. So for now, in this question, we're going to say, let's use the Bronsted-Lowry definition for an acid and a base, where an acid is a proton donor and a base is a proton acceptor. So let's take a look at A. So we're starting here. Okay. So with A, let's look at the left side of the reaction. Ammonia, NH4+, plus cyanide, Cn-, forms HCN and NH3. So you should be pausing the video and taking a look at what is acting as a proton donor and what is acting as a proton acceptor. Pause the video and think about it. Okay. On the left side, we see that NH4+ has 4 sources of hydrogen, and if we look on the right, the ammonia on the right has 1 less. So from the left to the right, we can see that we have donated a proton. So this on the left side would be our acid. Let's look at the flip side. We see Cn- had no sources of hydrogen, and now on the right side, it has gained a hydrogen. So we can say that it acted as a proton acceptor in this reaction. Therefore, this is our base. Okay. Now, the interesting thing about this is that now, since we're in Chem 102, we can go in both directions now. We can go in both the forward direction and the reverse direction. And we can see that this question is asking us about conjugates. So conjugates are introduced when reactions can go in both directions. So let's take a look at this reaction going this way towards over here. So we can see then that HCN is then going to lose a proton. Do you see that? So HCN has 1 proton, and then going this way, it has lost a proton. So we don't call it straight up as an acid. We say that it is the conjugate acid. The conjugate acid of Cn-. So we would say that Cn and HCN are conjugates of each other. So let me write that down. These two are examples of conjugates. Okay. So those two are example of conjugates, where HCN is the conjugate acid and Cn- is the conjugate base. Okay. So those are conjugates. And we can say then, if we look at the left side again once more, or the right side rather, we can say NH3 is over here with three protons, and on the left side we see that it now has 4 protons. So it is acting as an acceptor a proton acceptor, which would make it a base. But we're not going to call it just a normal base. We're going to call it its conjugate base. So these would be examples of conjugate acid-base pairs. So we have NH3 is the conjugate base of NH4+. So another way of saying that is that ammonia is the conjugate base of ammonium. Recall that this is ammonium. There's two M's in ammonium. I gotta put that. Ammonium. Actually, I don't think there's two M's. I think it's just one M. Ammonium. Excuse me in my spelling. Okay, so NH4+ and NH3 are examples of conjugates of each other, okay? Where NH4+ is the conjugate acid and NH3 is the conjugate base, okay? All right, so that does part A. So all we have to do, using the Bronsted-Lowry definition, is to look at what is acting as in a proton acceptor, that would make it a base, and what is acting as a proton donor, and that would make it an acid. Okay, let's continue with B. Okay, so we see then that this source here of CH3N has no protons, and on the right side we see that it has gained a proton. So that would mean that it's acting as a proton acceptor, which would make that a base. Here's the cool thing. Since we know that is the base, then we can say that the other is the conjugate acid. Because if we were to do that reaction in reverse, we would see that this has a proton source, H+, and then it is going to release that, acting as a proton donor to form CH3N. Okay, so the good thing is if you know what the base is, then you know what its conjugate acid is. With the flip side, we could see here that H2O has two hydrogens, and on the right is only one. So it is acting as a proton donor, which makes that an acid. And we can say then from H2O to OH-, then since this is the acid, then OH hydroxide must be its conjugate base. Okay. So just to recall, if we were to go in the reverse direction, that OH- would pick up a proton as an acceptor to form H2O. Okay? That is why we're calling it a base. It's a proton acceptor, and in particular, it is the conjugate base of water. Sometimes you'll see it written like this. You'll see that H2O, OH-. These two are examples of a conjugate base pair. Conjugate pair, a conjugate acid-base pair. Meaning they are one proton from becoming each other, right? So if H2O loses a proton, it becomes hydroxide, and if hydroxide picks up a proton, it becomes water. So this is what we call a conjugate acid-base pair. Okay. All right, so let's look at C. Make sure you pause the video and try to predict the answers yourself. Okay. Let's take a look at phosphate first. PO4 3-, we can see there, and it's picking up a proton over here. Therefore, it's acting as a proton acceptor, which would make that a base. And because that is a base as a proton acceptor, we know that HPO4 2- must be acting as its conjugate acid. Alrighty. And finally, we know since we have HCHO2, there's one proton source over here at the beginning, and we've now lost that source. So then it is acting as a proton donor. So this would be a donor, which makes it an acid. And on the right, if you were to do the reverse reaction, it would be picking up a proton, which would make that a conjugate base. Okay, so really quick recap. We are talking about the Bronsted-Lowry definition of an acid and a base. Acids are proton donors. So on left to right, if we see that we are losing a proton from left to right, or from right to left, depending on the direction you're looking at, it would be acting as an acid if what you're looking at is donating a proton. The base side is if you are accepting a proton. Okay, this will take some practice to get the hang of, but this is a very important process that we will be using for the remainder of the course. So get very comfortable with the concept of conjugate acids and bases, especially for those of you who are going on into any further chemistry. Okay? So, very important you get this. Make sure that if this doesn't make sense, you do plenty of problems, or you come to office hours to Dr. Fenton or I, and we can help you out with it, okay? All right. Hopefully that was helpful. See you in the next video.